if we think about what we know about velocity versus time graphs, what do we know about the acceleration of an object? The acceleration is any time we have a speeding up or slowing down. Good. Anytime we have a change in velocity. So acceleration is really any time we have a change in velocity. And we kind of use the word accelerate to mean speed up. And that's partially true. But any sort of speeding up or slowing down is considered an acceleration. Bless you. And so sometimes we use the word decelerate, right, to think about what is happening when we slow down. But in all reality, acceleration is any sort of change in velocity. Acceleration can be both positive or negative. Sometimes we get to this misconception of negative acceleration always means we're slowing down, and that's really not the case, okay? Do you remember the rule that I gave you for the sign of acceleration? Okay, the rule for this is anytime an object is slowing down, our velocity and our acceleration have opposite signs. Did we talk about that? Mm-hmm. Okay, so anytime our object is slowing down, our velocity and our acceleration have opposite signs. So it's true that most of the time objects are moving forward, and if we're slowing down, that would mean our acceleration is negative. So that's not a bad conception, but it's not true all the time. Because if I'm moving backwards and I'm slowing down, my acceleration would technically be positive, right? It would be a positive acceleration. So we prove that, and we can prove that with mathematically this equation. So the little line over the A, that just means average. Okay, it doesn't mean repeating or anything like that. It just means average. I'm not going to write that line over there very often because we're always going to be calculating average acceleration. So it's just not something I write. I annotate it once because your book kind of labels it like that, but I don't think it's super necessary. Remind me again, what does this triangle mean? Change in, or final minus initial. And so we have change in velocity over change in time. In all reality, there's hardly ever, I'm going to say like less than 1% of the time that we're going to have an initial time and a final time. Most of the time, it's just going to say it took us 6 seconds to do it, and that's our time. So you'll a lot of times see me write the equation, acceleration equals change in velocity over time, just like that, very simply, okay? That is an equation that I think should go on your equation sheet. So you might want to grab out that yellow sheet I gave you for your equations and throw that one on there as well. Acceleration equals change in velocity over time. Oops. And then if I was going to identify the units for acceleration, velocity is measured in meters per second. Time is measured in seconds. So it looks like this, meters per second, or meters per second squared. Right? That's the most common unit we'll use for acceleration. In all reality, our acceleration unit could be any sort of distance divided by time times time. Right? It could be kilometers per day per hour. Right? It could be meters per hour per second. It could be any of those things, because what this is telling us is that for every second that goes by, our velocity is changing by that many meters per second. Okay, so it could be a lot of different variations of that length over time squared, or length over time times time type of unit. Okay? Let's just try an acceleration one real quick here. I don't know that we'll even need to do both of the ones that are listed, but let's go ahead and just try one here. We need to get really used to and really comfortable with identifying our variables from the numbers given in our equations. In our written problems, okay? In our word problems, we need to be able to pull out those variables. So this says, during a race, a sprinter increases from 5 meters per second to 7.5 meters per second over a period of 1.25 seconds. What's my acceleration? Okay, I've got to start identifying what's velocity, what's time, what's acceleration. Are they initial or are they final? Those types of questions I got to ask myself. So if I was going to just identify this number first, 5 meters per second, what is it telling us? Initial velocity, and we just label it as V sub I for initial velocity is 5. Okay, that means 7.5 has to be what? My final velocity. How did I know right off the bat if that it was velocity? The units, right? The units need to be indicators for us of the type of variable that it is. Then we can identify, is it start or finish, okay? And then 1.25 seconds has to be my time. And my acceleration is what I'm solving for, so I'm going to let that be my question mark. Okay? Then I just go plug them into the equation. acceleration equals change in velocity over time. And we know change in is always what minus what? Always final minus initial. It's sometimes habitual for people to just go, oh, we're going to do 5 minus 7.5 because that's the order they come in the problem. But that's not how it works, right? It's got to be final velocity minus initial velocity over time. And so that gives us an acceleration equal to 2 meters per second squared. Okay? Does that fit our rule of thumb? Right? Where we were speeding up, so our acceleration and our velocity should have units that are the same. Right? They should have identical, I'm sorry, not units. They should have signs that are the same. So my velocity is positive and I'm speeding up, so my acceleration will also be positive. Okay? Let's do this next one real quick here. I think I have them all printed for you, so it should go pretty quick, okay? It says Marissa's car is moving at a speed of negative 28.6. That negative got cut off onto the wrong line there. So negative 28.6 meters per second. She slows down to a speed of 24 meters per second during a period of 3.2 seconds. What is her acceleration? Okay, so this time, what's the negative telling us? It's moving backwards, okay? So negative 28.6 is my VI, right? Initial velocity. My final velocity is negative 24. My time is 3.2, and my acceleration, again, is what I'm solving for. It won't always be that we solve for acceleration. That's just kind of how it worked out here. And so what happens when I've got a minus, a negative? They're gonna end up being added together. Okay, so negative 24 plus 28.6 divided by 3.2. I got an acceleration equal to 1.44 meters per second squared. Okay, mathematically, are we getting that to come out okay? Is that what we had? Okay, very good. Remember to do the numerator first, then hit enter before we go to the denominator so that your calculator does order of operations correctly. Okay? So let's review here. Acceleration and velocity are not the same thing. Velocity tells us the rate at which our position is changing. So it's how many meters per second go by. And then acceleration tells us the rate at which our velocity is changing. So let's walk through a really simple velocity and acceleration problem here so that you can visualize a little bit. Okay, so let's say I have an object moving 10 meters per second. Are you with me so far? 10 meters per second. And I have an acceleration of 2 meters per second squared. That would mean after 1 second goes by, now my object is moving 12. Another second goes by, now my object is moving 14 meters per second. Another second goes by, now my object is moving 16 meters per second, right? Its velocity is increasing by 2 meters per second every second, right? That's what that acceleration means. Meters per second per second. Okay, let's try this one here. A car is moving 75 kilometers per hour, comes to a stop in 5 seconds. What's my average acceleration? Do we see a red flag here? A problem, right? The units here. We do want our units to match, right? If at all possible, we want our acceleration to be meters per second squared. So that means our velocity needs to be meters per second. Do you remember the conversion to go from kilometers per hour to meters per second? Yes, that's half of it. 3.6. Very good. Very good. Divide by 3.6. So let's run that calculation. Right? We're going to divide that by 3.6 to get it to meters per second. And that gives me 20.83 meters per second. Okay? What does it tell me now? What variable does that sit with? What type of variable is it? Velocity initial, velocity final. Right. Initial velocity is 20.83. What does it tell me here when it comes to a stop? My velocity final is 0. Good. And then my time is 5 seconds. So I'm going to set it up 0 minus 20.83 over 5. And that gives me an acceleration equal to negative 4.17. Nope, 4.17. Sorry, I rounded wrong. 1.17 meters per second squared. Does that match our rule of thumb? Did we expect our acceleration to come out negative here? Yeah, because we're slowing down, right? Okay. Okay, if my acceleration of an object is 0, does that necessarily mean that my velocity is 0? No, right? I'm seeing a pretty consensus here for no, which I would agree with. But what's an example? If I'm at a constant speed, right? If I'm at a constant velocity, my acceleration is 0 because my velocity is unchanging. But it does not necessarily mean that my velocity is 0. Okay? What would my acceleration be if I was at rest? Also 0, right? So I would have that situation as well. Okay. All right. Now, I need you to get your equation sheet out because I'm going to give you the big 3 equations that we're going to use. These are ones we're going to use all year long. Okay? And I call them kind of the big 3. They are called your kinematics equations. Okay? Kinematic equations for constant acceleration. But if I were you on your equation sheet, I would write kinematics and then give a space for 3 of these equations to go. Okay, because these are big. These are the ones we're going to use all the time. And I'm probably going to have you label them 1, 2, and 3. Because a lot of times I'll say, oh, you need your first kinematics equation. Or your second kinematics or whatever. So this right here would be kinematics equation number 1, right? This was your first kinematics equation. VF equals VI plus AT. Are those all variables that we seem familiar with? Yes. Yeah, right? And I'll show you one other thing. This equation and the equation we just learned are identical, right? They're just rearranged because if acceleration is equal to velocity final minus the velocity initial over t, and I rearrange to solve for VF, I multiply by t, add VI, that leaves me VI plus t times A equals VF. Isn't that exactly the same? All right, those equations are identical. I just like this version better. Okay, so you're going to hear me use that version a lot more. Okay, so you don't need to write that down. You don't necessarily have to recognize that, but I just wanted you to see that those 2 equations we just used are identical. Okay, VF equals VI plus AT. So this would be what I call our first kinematics equation. Okay. These equations that I give you, these 3 that I'm going to give you, are only valid if you know that you have constant acceleration. So if your acceleration is constant, you can use these equations. And of course, all the problems I give you, that's going to be the case. But here's a case where acceleration would not be constant. If I sped up, then I slowed down, then I stayed still, then I backed up, then I did whatever. I cannot do all of those segments of my motion in one equation. I have to solve them in separate parts, right? So if I sped up, I solve whatever I need to for that portion of my motion. And then if I slowed down, I solve that portion of my motion. And then if I stayed still, I solve that portion. I can't throw them all into one equation. That's just how it works, okay? So there's that equation right there. I think we can, what do you think? Can we skip past one of these? If it's the same type of equation we just saw? Or you want to try it? I think we can skip past. It's really the same as what we just did, right? Here's my initial velocity. Here's my acceleration. Here's my time. It's asking me now to solve for my final velocity, right? So it rearranges a little bit. We see we're going to have to convert there. But I want to make sure we get time to get to all 3 of our equations today. So I'm going to skip over that one, okay? Second equation is this. X final equals X initial plus VIT plus 1/2 AT squared. They get a little more intense as we go on here. What are these variables right here? What do they represent? Do you remember? Displacement, good. So these would both be measured in meters. Okay, those are displacements. And so they would be measured in meters. Okay, one thing that I want to point out about this equation is that it's only the t term that is squared. Okay, it's not the whole 1/2 times a times t. We don't square the whole thing. It's just t that's squared. So it's multiplied, right? 1/2 times a times t squared. This one is an initial velocity times t. This is just initial displacement. Now, down here, I wrote this little extra thing. It says most of the time xi, or initial displacement, can be 0 since it's our starting location. That is really true. 95% or higher of the time, our initial displacement is 0. Because we don't care about what happened before. We only care about what happens during our time interval. So if it says it moved 150 meters, that is our x final, and our x initial is just 0. So a lot of times, this is going to just get dropped out of the equation, right, if that's 0. Okay, so let's go ahead and try one here with this equation. A train accelerates from rest at a constant rate of 3.15 meters per second squared for 1.57 minutes. How far does it travel in this time? Okay, so let's start just picking out numbers from our problem here. Okay, what's the first thing I see? Okay, I see acceleration here. Because it's meters per second squared, I know it's acceleration. So I'm going to come over here and make my list. Right, A equals 3.15. What other numbers do I see? 1.57 minutes. Do we see an issue there? It needs to be in seconds, right? Because my acceleration is meters per second squared. So I'm going to go ahead and convert 1.57 minutes to seconds. And we do that by doing what? Multiply by 60. That gives me 94.2 seconds. Right? Now let's see, what's it asking us for? How far does it travel? Displacement, right? We're asking how far. So that means we're solving for x final. Okay, I think there's one more piece of information from the problem that we're missing. It starts from rest. It accelerates from rest. So what variable does that go with? It is going to be equal to 0, but which variable? Velocity initial is 0, right? It starts at rest and it starts to accelerate. What about our xi, our initial position? Do we know anything or need to know anything about our initial position? No, we just are going to say that it's 0. Remember, because what I talked about, we always set the origin at the beginning of our motion. So we're starting our origin at that 1.57 minute, the beginning of that time interval. Let's go ahead and start plugging it into our equation, right? You're using this second kinematics equation. X final equals x initial plus VIT plus 1/2 AT squared. Okay. X final is what we're solving for, so I'm going to leave that. X initial is 0. Initial velocity is also 0. And what's anything times 0? 0. So I'm just going to not even include writing down the time, right? Because it's anything times 0 is 0. Okay, plus 1/2 A times T squared. All right, and then I just run the math. And I get a final displacement. I guess I would like for you guys to run it too, just so that you make sure you feel comfortable using that. But I got a final displacement somewhere around 13,976 meters. Okay, mine actually came out to 75.98. I'm going to go ahead and round that up. I'll give you a little minute head start here, and then I want you to try it on your own. Did you guys recognize here that we need two different steps? Right? It asked us for acceleration and for our final displacement. You can't use any of your kinematics equations without acceleration. Acceleration is a variable that's in all of them. So we have to do acceleration first. And so I found an equation that had, all the things I had and then the thing I needed, which was the first kinematics. And I solved for A, which I got to be negative 6.31. And then I went forward to move and solve for X final. I could have either chosen the second or the third equation to solve for X final. Did you guys pick that? You could have, you haven't even gotten the third equation yet. Okay, never mind. So you would have used the second to solve for X final, okay? So your equation should be set up something like that. And so I got an X final equals 50.48 meters. Okay, so here is our third kinematics equation. Right, this one is number 3. It's velocity final, and that term is squared. The equation tool doesn't have it written super clearly, but it's velocity initial squared plus 2a X final minus X initial. If you prefer to write out the delta like that, do it like that. That's fine. Doesn't matter. Okay. I want you to take a look at your 3 equations now. Kind of look at your kinematics equations together. There's 2 variables that are found in every one of them. What are those 2 variables? Velocity initial and acceleration, right? Those are found in all 3. The second equation, what's it missing? What's the second equation missing? Velocity final. And what's the third equation missing? Time, right? So that's okay. It's missing time. So you have a little flexibility. If you're not given time in your problem, you might need to use this equation to help solve for something. If you're not given a final velocity, you could use your second equation. So it gives you a little more flexibility as to what you're given in your problem and what you need to use. Okay, so let's try one here. A car starts at rest and speeds. Actually, I want to go to this next one. The next one's a little more complex, so I want us to do this one actually. Okay, so I'm going to skip over that one. A car accelerates at a constant... Nope, I changed my mind. I'm the worst. I changed my mind. Okay, I can't make up my mind. I just can't. Okay, I want this one. All right, we're going to do this one because I know it uses the third equation, and we need to practice with that one. So, a car starts at rest and speeds up at a rate of 3.5 meters per second squared. How far will it have gone when it is traveling 25 meters per second? So, starts from rest, gets up to a speed of 25 meters per second. We want to figure out how far did it go during that time. Okay, so let's start picking out some variables. Starts at rest, that's your first one. And that's got to be initial velocity. What is this 3.5 here? It's got to be acceleration, right? Because of the unit itself, it's acceleration. How far will it have gone? So what does that mean I'm solving for? Displacement. So X final is my question mark. And what's this 25 meters per second? Velocity final is 25. So now I've got to check my equations and say, do I have an equation that has initial velocity, final velocity, acceleration, but not time? Right? And I think it's your third one. Right? So let's go ahead and plug that in. VF squared equals VI squared plus 2A X final. What do we know about our initial position? Did it tell us anything about our initial position or XI? No, so we just assume it's 0, right? And you can either write in minus 0 or you can just leave it off, right? Because it's not going to change anything. So I just like to leave it off, okay? 25 squared is 625 equals 0 squared, which just drops out, 2a times x final. Do we have a problem here? We've got two variables. No, we don't. No one pointed that out to me earlier, that I just left acceleration right out of the problem. Okay, how about we put a 3.5 here? Because we know that's what it is. Let's do it. Okay, sorry. All right, so 3.5 times 2 is 7xf. So now I'm just going to take 625 divided by 7, and I'm going to get a final displacement of 89.3 meters. There we go. Much better.